Welcome to Yadyan. In this video, we discuss about cupping test in sheet metal, how it is performed, and why it is needed. Friends, this test also known as Ericsson cupping test, and it is very significant test to know the tactile properties of a metal. So, whenever we use a forming processes like deep drawing or a drawing process, then the tactile property of a material is a very important one to know whether it will underperform or undergo the forming process or not. So in this test, we apply a punching force in the sheet metal of thickness 0.2 mm to 2 mm, and then we do a visual inspection on the test specimen which we have used to see whether any cracks or deformity has been formed or not. The force applied on the sample is displayed by the gauge which is fixed on the equipment. So there are various types of equipment available in the market with the gauge, without the gauge, and manual also. So the formability, as we all know, is the ability of a sheet materials to be formed into specific shape or configuration. So in order to form a specific shape or a configuration, the formality of a material should be very good. So this formability depends on strain hardening coefficients, strain rate sensitivity index, plastic strain ratio, strain distributions. So friends, if you have not subscribed to Yadyan, please subscribe to Yadyan. This is the general arrangement how the test specimen is fixed in the die, and we apply force to keep in place this test specimen, and then we apply a punch force from the top with this circular punch, and this is the general arrangement and equipment to perform this test. We have this gauge on the top of it where we can see the applied force. Earlier, there were a punch actuating wheel where we rotate this wheel to apply the force. And we have die and punch here. You can see this is a holding ring. And here we have mirror for viewing the crack, and this was the earlier arrangement. Then we have nowadays with the gauge on the top of it so that we can see the force value. This is the punch, flat punch, and the hemisphere punch with the die. And these are the tools to perform the test. Here you can see the forming limit curve, and this is using hemispherical cupping die. Then we have this forming limit curve with the flat cupping die which has been obtained. So this is the test specimen that we obtain after performing the test. So here we do some visual inspection, and here we, if we see this kind of cracks, it's known as radial cracks. This is circumferential cracks. And here you can see this visual inspection of this dome gives us some rough idea about how the rough appearance is, and large grain size. If it has very large grain size on it, we can very easily visualize it. Then we have radial cracks. That means this has the equal strength in all directions. Then the third one is the circumferential cracks for anti-stopping property of the seat. And if we have one direction crack, then it has a very good ductile property only in particular one direction, and in other one direction it has not equal ductile property. So due to ductility in different direction, we cannot use this seat in all directions for forming process. We need to know the proper direction, in which direction only we can use the forming process. If we use that seat in another direction, then it will fail to form the shape and it will generate the crack. So that is not good for the forming process, and that's it. We cannot use that material, we cannot use. So the material which has equal ductility in all directions, that is a very good and proper material to be used for the forming process. Then we have this standard chart established by Ericsson, and this here you can see this is the thickness of the sheet in mm from zero point 0.2 to 2.4 mm. Then here we have depth of the cup in mm, 6 mm to 15 mm, and here you can see for 1 mm thickness we can go up to 8 mm for a zinc. Similarly, for 2 mm thickness for a brass we can go even above 14 mm. So if you go from bottom to top, the depth of the cup increases. That means ductility of a material increases. Even with the higher thickness, we get a very good ductility. So that means these top materials are very good in order to use for deep drawing or drawing process or for forming process, manufacturing process. So brass, copper and aluminum are the excellent one to be used for the forming process. However, brass and copper are more costlier than aluminum. So mostly if you see components are made of aluminum, which are cheaper compared to copper and has a very good ductile property, almost nearer to the copper. And wherever there is a need of better heat transfer, then we can use copper because it has a very good heat transfer properties. But wherever there is no need of heat transfer and there is no need or any requirement, then we can go with aluminum so that we can reduce the cost of raw material. And aluminum is very easily available at a very cheaper rate and larger quantity. So here, as you go down, the ductility of material decreases. So this is the standard chart that we can use for considering drawing or deep drawing process for this material. And for any other material, if you want, you can perform this test and establish the curve within which you can use this material for such kind of manufacturing processes. So friends, I hope you will like this video. Thank you very much and happy learning.